What did we cover in the last class? I typically discuss that a little so that our connection with the previous lecture is formed and help us build on what we have covered in the last class in a better way. So in the last lecture, we looked at what is digital signal processing um, and how does it compare with the analog counterpart, both in terms of implementation as well as advantages of one over another, and what are the features which are offered by DSP operations. Then we looked at some concepts of signals, including continuous time, discrete time, and continuous valued and discrete valued signals. And towards the end, we covered what are deterministic signals and random signals. These were the readings from the previous lecture. I hope we have all gone through it and done that. Chapter 1 Introduction, Section 1.1 and Section 1.2 along with their subsections we were supposed to read so that the contents of the lecture 1 are covered and understood properly. Okay, so coming to the contents of this lecture, let's begin by looking at the lecture objectives. In this lecture, we will look at the concept of frequency in continuous time as well as in discrete time domain. So we are familiar with the concept of frequency in continuous time. So we will begin with that. We will just take note of what are the concepts of frequency in continuous time, and then slowly and gradually look at how these concepts play when we move into the discrete domain. And this will give us an insight into how the concept of frequency are different in both the domains, continuous domain and the discrete domain. So this is an important part of the course because it forms the foundation for several topics which we will cover throughout the course. And towards the end of the lecture, we will also look at the properties of periodicity and the frequency range in which we are allowed to operate when we are working in discrete time. One thing to note here is that occasionally you will see that I am using the words discrete time sinusoids. So one might wonder why I am not talking about discrete time signals and I am just focusing on discrete time sinusoids. The reason you may be well aware of is that in Fourier analysis from our course in signals and systems in the last semester, we have understood and we know that all signals are composed of sinusoids. So if we can study the properties of sinusoids, it is very easy to scale those to any form of the signal. So that's why occasionally you will see me and the book as well talking about sinusoids and then generalizing the properties to other signals as well. Okay, so let us move into the concepts of frequency, and we begin by considering a continuous time sinusoid. So a sinusoid can be a sine signal or a cosine signal, but we have here chosen a cosine signal. It can very easily be sine signal or a complex sinusoid as well. So we know that in continuous time sinusoid, we call a signal as x, and depending on the independent variable time represented by small t, then this is equal to the amplitude A times the cosine function of omega as a frequency times time plus the phase, which here is represented by Greek letter theta. So in a sinusoid we have three variables: the amplitude, the frequency, and the phase. Because we are looking at the concept of frequency, so we are more concerned about omega. So what we can do is we can set up value of A as equal to 1 and the value of theta as equal to 0, which is defined here as A equals to 1 and theta equals to 0, which makes A cos omega t plus theta simplified to cos of omega t. And because we know omega is equal to 2 pi into frequency, so cos omega t can also be written as cos 2 pi f t. Now the units of omega and f are given here as omega is radians per second and capital F is cycles per second or hertz. So we will take these definitions to understand the concepts of frequency in continuous time sinusoids. Okay, so here what we are going to do is to look at three properties of the frequency or the analog or continuous time sinusoids we are familiar with. And please note that there will be nothing new. All these three postulates or properties are something we are aware of. We are just making them come into our notice again, so that when we study the discrete time sinusoids, we can easily compare the concepts of frequency in both domains. So let's begin by looking at what is the postulate 1. Postulate 1 for continuous time sinusoid says that a sinusoid with a periodicity capital T repeats itself. So if a signal is periodic by capital T, then the value of the signal after every capital T will repeat itself. This is a commonly known periodicity property which exists for any sinusoid which is there in a continuous time domain. And this is not a new concept to us, but we have just make a note that yes, the periodicity exists for continuous time sinusoids and the signal repeats itself after a capital T, where capital T is the periodicity of a signal. Postulate 2 is also very obvious. It says that continuous time sinusoids with different frequencies are distinct, and we know this. So for example, a continuous time sinusoids of 25 Hertz will be different from a continuous time sinusoid of 125 Hertz or 1025 Hertz or whatever. In fact, if I provide you a waveform of a cosine or a sine signal, and I simply plot the x-axis and the y-axis and ask you to figure out what is the frequency of that sinusoid, I am sure all of you can use simple measurements to come back with the frequency of that sinusoid, and all of you will come back with the same number. if that sinusoid is 35 hertz, all of you will come back and say this is 35 hertz, and it will not happen that half of the class is saying that it is 35 hertz and rest of the class is saying it is 135 hertz or 150 hertz or something like that. This will not happen. Why? Because continuous time sine or cosine signals, they have this property that as you change their frequencies, the waveforms change. They expand or they compress based on whether we are decreasing the frequency or increasing the frequency. But for every frequency, there is a distinct waveform. So this is the second postulate which we notice and we observe is there for a continuous time sinusoid. And somewhat related to postulate 2, there is postulate 3, which says that increasing frequency of a continuous time sinusoid will always increase the rate of oscillation. The rate of oscillation is the time it takes for the waveform to move from the highest value to the lowest value. This is the rate of oscillation. So in a cosine of amplitude 1, the highest value is 1 and the lowest value is -1. And we know that as we increase the frequency, the time it takes for a waveform to move from the highest point to the lowest point start decreasing, thus increasing the rate of oscillation. And the observation is that as we keep on increasing the frequency, the rate of oscillation also keeps on increasing till infinity. So it never happens that you increase frequency and the rate of oscillation stops increasing or start decreasing. This never happens. So looking at the postulate 2 and postulate 3, the postulate 2 says that all continuous time sinusoids with different frequencies form distinct waveforms, and postulate 3 says that as we increase the frequency, the rate of oscillation for the signal increases. Combining that makes us realize that the frequency range, allowable frequency range when we are working in a continuous time domain is infinity, is basically 0 to infinity. So you can use any frequency you want because all frequencies will generate distinct waveforms and are there to be used for any purpose you want. And for mathematical symmetry, we take the negative frequencies as well. So the frequency range, allowable frequency range for continuous time domain becomes -infinity to +infinity. So that much width, that much room we have in continuous time domain when we are using the frequency. Right. So now what we